right, we're down to our last two sections of the year, and we're starting one of the two sections here that we will cover in Chapter 12. And if you look on page 765, that's where we will be starting at, 765. This is called Modeling Inverse Variation. Now, there's three major things that I'm going to ask you to do in this section. I guess three goals of things that you need to be able to do. You're going to need to be able to identify direct or inverse variation from an equation or a table. So that's one major thing. The second major thing you'll have to do is be able to, if you have inverse variation, write an equation for it, which I will show you how to do. And then the third thing we need to be able to do is sketch inverse variation functions without using a calculator. So again, this is another section where you're going to have some basic sketching to do, and I won't let you use your calculator. So to do all that, I think there's a few things we probably should discuss and review. So this isn't something that's coming out of left field at you. So before we discuss inverse variation, let's review what direct variation is. And direct variation is something that we would have done early in the year. These direct variation, in fact, would be, I'm just going to write it in here, direct variation is linear equations. Okay? And here's the example that I always used early in the year when we talked about linear equations and direct variation. Direct variation is when both x and y vary in the same way. It's like my lawn mowing example that I've used over and over this year. If x is how many times you mow my lawn, and y is what you are paid, let's say you get $20 each time, if you mow my lawn once, I'd give you $20. If you mow it twice, I gave you $40. If you mow it 3 times, I gave you $60. And what I'm trying to show, or what I'm trying to say here, I can probably make it in a table. And let me make it in a table right here. Okay, so x is the number of times I mowed, and y is the amount paid. So I'll just put dollars and times mowed. Okay, if I mow once, I get $20. If I mow twice, I get $40. If I mow 3 times, I get $60. 4 times is $80, and so on. You notice if I double x, I doubled the pay. If I tripled x, I tripled the pay. If I quadrupled x, I quadruple the pay. That's a linear pattern. Another way to look at it would be if I go up 1 for x, I add 20 for y. If I go up another 1 for x, I add 20 for y. This is a linear pattern. It's a direct variation pattern. The equation for this would be y equals 20x. Remember, we did that last, or actually in section 10.8. I go up 1 for x. When I go up 1 for x, I keep on going up 20 for y. So my slope is 20. I'm rising 20 for every run of 1, and my y-intercept would be 0. If I don't mow, I get no pay. My b value is 0 here. All direct variation situations can be modeled by y equals a times x. This looks in slope-intercept form, but you notice b must be 0. So direct variation would be slope-intercept form, and maybe I could write that in, but b must equal 0. Okay, so in other words, when I do slope-intercept form, let me write that out. This here, my b value, must be 0 for a direct variation situation. Okay? So now that we've reviewed direct variation, let's talk about what inverse variation is. Okay, direct variation, as you recall from my lawnmower example, if you double the amount of times you mow the lawn, you double the pay. If you triple the amount of times you mow the lawn, triple the pay, and so on. All right. Inverse variation is just what it sounds like. It's inverse. There's an inverse relationship. So unlike direct variation, where if x is doubled, so is y, and so on, in inverse variation, if you double x, y would be half as much. If you triple x, y would be 1/3 as much, and so on. Now, maybe to wrap our mind around that, I can make up a simple real-life example of that. So let's say, here's a real-life example of inverse variation. You have 100 pieces of candy. You get to keep them all for yourself. You have 100 pieces. So let me make a table of that. Okay? So here's the number of people getting candy. And Y is amount of candy. Okay, so if you get all the candy, you get all 100 pieces. Well, let's say we double the amount of people getting the candy. In other words, you got to share the candy with someone else. Well, if you share the candy, you're only getting 50 pieces each. So does this make sense? You doubled the amount of people that get candy, but then the Y value is now half as much. Let's say we decided to split the candy among 4 people. If the candy is split among 4 people, we have quadrupled the amount of people that are splitting the candy, but everybody is only going to get 1/4 as much. That's inverse variation. If I have 5 people sharing the candy, everybody's only going to get 20 pieces. So while the amount of people is 5 times greater, the amount of candy everybody gets is 1/5 as much. That would be inverse variation. Now the equation for this, it's pretty easy to find. Do you notice when I have this table, if I multiply my XY pairs, 1 times 100 is 100, 2 times 50 is 100, 4 times 25 is 100, 5 times 20 is 100. Whenever you have a table, if you can multiply your XY pairs, if they continually work out to be the same thing, you immediately know it's inverse variation. And all we have to do to write an inverse variation equation, it always is going to take this form. It's going to be Y equals A. Now, A is that number that we always get when we multiply these out over 100. And as I showed you, 1 times 100 is 100, 2 times 50 is 100, and so on. I kept on getting 100. My equation is Y equals 100 over X. Let's see if that works. If 2 people share the candy, if X is 2, 100 divided by 2 is 50, just like my table said. If 5 people share the candy, 100 divided by 5 is 20. So there is my equation. So inverse variation equations always take the form Y equals A over X, where A is the amount that you get when you multiply the XY pairs of your inverse variation table. If you can ever write an equation in this form, then it must be an inverse variation function. All right. I think what we should do here, let me move on to my next slide. Okay. So when we look at some of these problems in our homework, let's do a few of these. And if you go to number 3, question number 3 through 14, it says, describing equations, tell whether the equation represents direct variation, inverse variation, or neither. Okay, so let me just write a little reminder here before we start doing this. Remember, if it's direct variation, that means it's linear, and I will have a slope and an x, but b is nothing. That would be direct. If I have inverse variation, that means the equation could be written in this form. So when I look at number 3, by just looking, I can tell it's direct. It says Y equals negative 2 times X. Well, that's definitely of this form. It's direct variation. Let's look at question number 4. I'm going to do this first. It says XY equals 1. And you might be like, well, wait a minute, that doesn't look like this or that. Okay, well, think about this for a minute. XY equals 1. If I divide each side by X, the x's cancel, Y equals 1 over X. This is definitely an inverse variation model. Another way I could have thought through that, think about this for a minute. If X times Y is 1, if I plug in 5 for Y, X is a 5th. If I plug in 4 for y, x is a fourth. You see how if whatever I plug in for x, y is the reciprocal of that amount. That's another way to tell that I have inverse variation. All right. Moving on to number 5. Okay. Number 5, I shouldn't have clicked that yet. Number 5 would be neither. And let's talk about why it's neither. You look at the equation. Number 5 says y equals x plus 5. Okay, well, first of all, I know it can't be direct because this is in slope-intercept form, and my b value must be 0 if it's direct, and it's not. So this cannot be direct. Inverse, can I rewrite this equation to look like this? Well, no. If you notice inverse variation, I must have x divided, or a number divided by x. I can't manipulate this equation to get into this form. And in fact, as x keeps on getting bigger, remember in inverse variation, if x gets bigger, y should be getting smaller. Well, let's try. If I put in 1 for x, y ends up being 6. If I double x, y should be half as big. Let's try. If I double x, 1 times 2 is 2 plus 5 is 7. Do you notice how y is not getting half the size or half the amount? This is definitely not inverse either. Number 5 is neither. Number 5 would be neither. Number 6, 6 said x equals negative 1 over y. Well, this one, let me see here. Let me multiply each side by y first. And that would give me xy equals negative 1. And let me divide each side by x. That gives me y equals negative 1 over x. Well, you can see that's definitely an inverse relationship. Okay, that's an inverse function. Okay, and I'll do one more with you. Number 7. 7 says x times y equals 5. Well, let me see. If I get y by itself by dividing by x, it's easy to see that this takes on that form. This is definitely an inverse relationship also. Okay? Let's go to numbers 28 to 42. They're going to ask you to write an inverse varying function with the given information. So the directions say, given that y varies inversely with x, use the specified values to write an inverse variation equation that relates x and y. Then find the value of y when x is 2. So they told you in the directions y varies inversely with x, which means this is inverse variation right away. And if it's inverse variation, it must be in this form. It must be in the y equals a over x form. And they told you in 28, if you look at question 28, x is 5 and y is 2. So where you see x, I replaced a 5. And where you see y, I replaced a 2. So I got to figure out what a is. So to find a, it's easy. Multiply each side by 5 real quick. And I get a is 10. Can you see that? If I multiply the left side by 5 and the right side by 5, I'll get 5's canceling here. And I get a equals 10. So since a equals 10, and this is an inverse variation equation, then all I got to do is replace a with 10. There's my equation for number 28. It's y equals 10 over x. They also want me to find out what value does y have when x is 2. Well, I can do that really easy. I can plug in 2 for x, and 10 divided by 2 is 5. So here's how I would write my equation, and here's what I need to do then to find out when x is 2, y is 5. Okay? And that's what we're doing in questions 28 to 42. So far in this video, I've identified what you need to do to identify whether an equation is inverse variation or direct variation. We've talked about how to write an equation if we know the problem is an inverse variation function. And the last thing we need to do is sketch, okay, because we will be doing some sketching on questions like 15 to 26. And so I think I'm going to go to that next here, okay? Sketching inverse variation equations. So to sketch, first of all, inverse variation equations have a basic form to them. And let me write that form down as I read and I go through this here in a minute. Inverse variation equations have this form. It's going to look like, and let me write it up at the top of the screen, y, let me get a bigger marker so this is easier to read, y equals a. Now you've seen this a many times, and then after we have a, okay, after we have a, and by the way, you might want to be looking, this might help out a little bit if you turn ahead to page 773, so I want to incorporate this a little bit ahead of time. We have a over x minus h, oh, that's not a very good h, plus k. Now there's certain elements of this equation that you're already aware of. Now a has a similar meaning to what we've done previously already. You know, we've had a lot of different sketching where a told us does the function open up or down, stretched or shrunk. It kind of tells us somewhat that here too, but a little bit different. If in these functions, inverse variation, if a is a positive number, our graph will end up in quadrants 1 and 3, which means up here and down here. If a is negative, my graph's going to be in quadrants 2 and 4, which are here and here. So the value of a, you can kind of, I guess you can still think of it as opening up or down. If a is positive, the graph will be up here in quadrant 1, but it'll also be here in 3, so it's opening up in 1. And if a is negative, it's opening down in here in quadrant 4, but it'll also be in quadrant 2. H and K tell me something also. Those things tell me what are called asymptotes. And you might be like, what the heck, all right? These can help me with my asymptotes. And I better make sure I spell this right. And I'm looking right now. I'm kind of embarrassed to say I don't remember exactly how to spell asymptotes. A-S-Y-M and P and totes. Okay, these help me with my asymptotes. Now, what is an asymptote? Well, to explain an asymptote, I better do a simple problem with you, and then I'll show you what the asymptotes are and what they mean. So I think I have an example here, and let me erase what I just put down so you can read my example. But anyway, there was the basic form. Let me get this out of there. There's the basic form. I'll give you a second to write that in your notes, or you can stop the video and write it in your notes. And let me erase this now, okay? Because here's the problem that we'll work on together. Y equals 2 over x. Okay, now you notice, based on what I had on my before I erased, I'm adding nothing here, and I'm adding nothing out here. Okay, so again, you got to think to yourself, what do I plug in here to make this 0 down here, and then this is 0. Okay, this is called my horizontal asymptote, and I got to plug in 0. Okay, here's what that means. That means that if my horizontal asymptote is 0, I basically have an imaginary line, and I'm going to draw that up right now. An imaginary line going right down the y-axis of my graph at x equals 0. I hope that shows up okay. All right. And then this tells me I have a vertical asymptote at 0, which means I have an imaginary horizontal line. Oh, I hope I said horizontal. Horizontal line at y is 0. Now, these lines are kind of borders that my graph won't cross. So now, let me erase those out because I got my asymptotes at 0 and 0. Okay, now let me make a table of these points. Okay, I'm going to just plug in some for this first one for you. If I plug in -4 for x, I get -0.5. If I plug in -2 for x, I get -1. If I plug in -1 for x, 2 over -1 is -2. I can't plug in 0. That's why I'm writing undefined. I can't divide by 0. And then if I plug in, you notice, when I plug in 1, 2, and 4, I'm getting the same numbers, just opposite sign. So if I plug in 1, I get 2. If I plug in 2, I get 1. And if I plug in 4, I get 1/2. Well, I'm going to sketch those points. Here's -4, -0.5 here. Here's -2, -1 here. And -1, -2 here. And then over here, in my first quadrant, I have the points 1, 2, 2, 1, and 4, 1/2. Well, when you have an inverse variation equation, which this is, and you sketch, you're always going to get this type of shape where it kind of looks like here that this was a exponential decay, and then this kind of looks like the mirror of that exponential decay, but these are not exponential decay. This graph is called a hyperbola, okay? And a hyperbola is always the kind of graph that you get when you're sketching an inverse variation function. And a hyperbola will always be in quadrants 1 and 3 if my a value is greater than 1. And my hyperbola will be in quadrants 2 and 4 if my hyperbola is less than 1. And when you graph these, or I should say sketch these, I would have you do these without a calculator, which means I'll probably have you list 6 points. I'll probably have you list 3 points on one branch of the hyperbola. This is called a branch. And then I will have you sketch 3 points as you sketch this, or graph 3 points as you sketch this on the second branch of your hyperbola. Maybe, I know this video is getting a little long, 20 minutes. I'm going to quickly do one more just to make sure that you have one more example you can see. Let me pause it real quick while I get my graph. Okay, so I'm going to look at number 7 on page number 769. We'll sketch this one together real quick too to give you a second example. Y equals -7 over x. So the first thing I notice here, remember, this is an inverse variation function, and those always have this form. So I'm adding nothing for k, and I'm adding nothing to x, which means my asymptotes, I got to plug in 0 to get 0 here, and there's nothing here. So 0 and 0 are my asymptotes, which means the following. Let me make this a little bit thicker so it's easier to read. Okay, I have one asymptote here. There's my vertical asymptote, and I got that because I had 0 here for x. And then I also have a horizontal asymptote, and that's because I had 0 here for k. All right, now I'm going to make a quick little table for myself so I can sketch. Now remember, since a is negative, my asymptote, my hyperbola will be up here in quadrant 2 and down here in quadrant 4. So I'm going to make a table real quick, and let me see. I'm going to plug in some easy things. I'm going to plug in, let's say, 7. I'm going to plug in, actually, -7. I'll plug in -1. I'm going to plug in, actually, -14. Let me do that because that'll be easy to do, too. So -14. -7, -1, and I'll plug in 0, 1, 7, and 14. Now, you might be wondering, why am I going with 7 and 14? Well, here's why. If you put in -14, -7 over -14 is positive half. And if you plug in -7, -7 over -7 is 1. And if you plug in -1, -7 over -1 is 7. 0 is undefined. I can't divide by 0. If I plug in 1, I get -7. If I plug in 7, I get -1. And if I plug in 14, I get -half. Okay, well, let me sketch these. -14 half would be here. -7, 1 would be here. And -1, 7 would be here. And you can kind of see this branch of my hyperbola is going to be something like that. And then here's 1, -7. And here's 7, -1, and 14, -half. And this branch of my hyperbola is going to be, well, I'm trying to draw this as best I can, something to that extent. And that's how we would sketch a inverse function, which would give us a hyperbola.